Hello everyone, I am Abhijit Lal, Assistant Professor, Department of EEE, Bhilai Institute of Technology, Durg. Today we are going to study about the Zener diode as voltage regulator. So, as we have discussed in the applications of Zener diode, the main application, or we can say that the major application of Zener diode is as voltage regulator. So, we will discuss about the introduction for that voltage regulator, then Zener diode as a voltage regulator, then we will see the analysis of the Zener diode circuits for different condition of voltage and current, and at last we will discuss some numericals. So, what is voltage regulator? A voltage regulator is a device that regulates the voltage level, that means changes the magnitude of voltage above or below the rated value, or we can say that reference value. So, it essentially steps down the input voltage to the desired level and keeps it at the same level during the supply. So, this ensures that even when a load is applied, the voltage does not drop. So, the voltage regulator is used for two main reasons, and they are: first one, to vary or regulate the output voltage, and second, to keep the output voltage constant at the desired value in spite of variations in the supply voltage. The two basic function of voltage regulator is it regulates the output voltage, decreases the level, or sometimes it increases the level also, and secondly, the most important is to maintain the voltage level in spite of the variations in the supply voltage. Even if the supply voltage is changing, the output voltage should remain constant. These voltage regulators we all see at our homes, at our offices, that which is connected with the air conditioner. So, what it does, or air conditioner or refrigerator, what it does is that if the input side is fluctuating, it gives the output or the voltage level, it keeps the voltage level for the appliances at a constant value. So, even if the voltage is fluctuating, our appliances are getting a constant voltage. So, this is the main working of voltage regulator. So, the voltage regulators are used in computers, power generators, alternators to control the output of the plant, whereas at the small level for domestic applications they are used for the refrigerators, for air conditioners, etc. So, now let us see the Zener diode as a voltage regulator. How Zener diode is used as a voltage regulator. So, a Zener diode can be used as a voltage regulator to provide a constant voltage from a source whose voltage may vary over sufficient range. So, suppose if the input supply is varying at a particular range, but the output voltage required is constant. So, for that the voltage regulator is used, and here we are going to study about the Zener diode as a voltage regulator, how Zener diode are used to regulate this voltages. So, the circuit arrangement for the Zener diode as voltage regulator is shown in the figure. In this, EI is the source voltage, resistance is connected, a Zener diode is connected in parallel with the load, and the load resistance is denoted by RL, and E naught is the output voltage obtained at the load side. So, we will see in how the voltage is regulated by this circuit. So, the Zener diode of Zener voltage Vz is reverse connected across the load RL, across which constant output is desired. So, as we have seen in the circuit diagram, the desired output is E naught. So, the Zener diode with a Zener voltage of Vz is connected in reverse connection with the load RL, and it is connected in parallel with the load. So, the series resistance R absorbs the output voltage fluctuations so as to maintain constant voltage across the load. So, here the role of the series resistance connected is to absorb the output voltage fluctuations, so that the constant voltage is maintained at the load side. So, it may be noted that the Zener will maintain a constant voltage Vz. As we all know, the Zener voltage is denoted by Vz, and it will be equal to E naught. So, what Zener will do is that it will maintain a voltage Vz which will be equal to E naught, which is the output voltage. So, across the load the voltage will be maintained at Vz so long as the input voltage does not fall below Vz. So, until and unless the input voltage decreases below Vz, the output voltage will remain as Vz and it is equal to E naught. That means the voltage showing at the output or we can say that at the load side. So, when the circuit is properly designed, the load voltage E naught remains essentially constant, that is equal to Vz, even though the input voltage Ei and the load resistance RL may vary over a wide range. So, here the main function of the voltage regulator is that even if the resistance RL, the value or the voltage across the resistance changes, or even if the input voltage Ei changes, but the output voltage E naught will remain constant equal to the Zener voltage Vz. So, let us take one condition, that suppose the input voltage increases. Since the Zener is in the breakdown region, the Zener diode is equivalent to a battery Vz. So, it is shown in the figure that the Zener diode is replaced with a battery source with a voltage Vz, and the current Iz is flowing through it, and the load current is IL, and the voltage which we are getting at the output is E naught, and the input voltage is Ei. So, the output voltage remains constant at Vz equal to E naught. So, the excess voltage is dropped across the resistance R. This will cause an increase in the value of total current I. So, the Zener will conduct the increase of current in I while the load current remains constant. So, here the concept to make the load voltage constant is that even if voltage or the load changes, so the excess voltage is dropped across the resistance which is connected in series. The total current gets increased, but the voltage obtained at the load remains constant. Hence, the output voltage E naught remains constant irrespective of the changes in the input voltage Ei. Now, let us see the second condition. When the input voltage is constant, but the load resistance RL decreases. So, what happens when the input voltage, that is Ei denoted by Ei, remains constant and the load resistance RL decreases? So, this will cause an increase in load current. So, the extra current cannot come from the source because the drop in R, and hence source current I will not change as the Zener is within its regulating range. So, the additional load current will come from a decrease in Zener current Iz. So, consequently, the output voltage stays at constant value. So, this is how for both the conditions the Zener diode maintains the voltage at the Vz, so that the constant voltage at the output E naught is obtained. Now, the voltage drop across R will be equal to Ei minus E naught, that is the input voltage minus the output voltage, that will be the drop across the resistance R, and the current through R will be equal to Iz plus IL. That means, the current flowing through R will be the summation of Iz plus IL. So, applying Ohm's law, we get the value of resistance equal to Ei minus E naught divided by Iz plus IL. So, this will be the value of resistance, series resistance connected in the circuit of voltage regulator. Now, let us study about the analysis of Zener diode circuits for different values of resistance, voltage, etc. So, the first step in analysis is to determine the state of Zener diode, that is whether the Zener is in on state or off state. So, any semiconductor device is having its two state, that is on state or off state. So, as we are going to study about the analysis, so the first step is to find out the condition or the state of Zener diode, that is for different values whether the Zener diode will be in on state or off state. So, after that the Zener is replaced by its appropriate, or we can say that equivalent model. So, knowing the state, that is on state or off state, the Zener diode will be replaced by its equivalent model. So, finally, the unknown quantities are determined from the resulting circuit. So, let us study about the first condition when the supply voltage E I and the resistance R L, which is the load resistance, are kept fixed. So, the figure is showing the circuit in which the source voltage or the supply voltage is E I, a series resistance R is connected, Zener diode is placed in parallel with the load R L, the resistance of load is R L and the output voltage is E naught. The first condition is that when the source voltage E I and the load resistance R L is kept constant. So, the applied voltage E I and load resistance R L is fixed. So, the first step is to determine the state of Zener diode, which can be determined by removing the Zener from the circuit and calculating the voltage V across the resulting open circuit as shown in the figure. Here what we have done is that the Zener diode is removed and the voltage is calculated across it, keeping the rest of the components, that is the series resistance R and the load which is having the resistance R L, the voltage is E naught and the fixed supply voltage is E I. So, here the voltage V will be equal to E naught and its value, mathematical value, will be equal to R L into E I divided by R plus R L. So, on solving the circuit, we will get the value of E equal to R L into E I divided by R plus R L. So, if the value of capital V is greater than V Z, then Zener diode is in the on state and its equivalent model is shown in the following figure. So, now the value, as we have obtained the value of capital V, so if that value exceeds the value or it is equal the value of V Z, then Zener diode will be in on condition, and if its value is below V Z, if it comes out to be below V Z, the Zener diode will be in off condition. So, the following figure shows the voltage V Z, where the current is flowing is I Z and the current flowing from the source is I, and the current I L is flowing towards the load. So, this is the circuit when the Zener diode is in on state. So, in on state, the value of E naught will be equal to V Z. So, as the Zener diode is connected in parallel with the output, that is a load, so the voltage obtained at the output will be equal to the Zener voltage, that is V Z, and the value of current I Z will be equal to I minus I L. That means, the current coming from the source towards load minus the current flowing in the load. So, where I L is equal to E naught divided by R L and I is equal to E I minus E naught divided by R. So, from this we can calculate the power dissipated in Zener diode, that is, it is denoted by P Z and its value comes out to be V Z into I Z. So, the power dissipated across or in the Zener diode when it is in on state, it is equal to V Z into I Z, where I Z is equal to I minus I L. Now, the second condition, when the value of V is less than V Z, and what happens here is that the diode is in the off state and it is shown in the figure that condition here is of open circuit. So, when the diode is in off state, it can be replaced by a open circuit. So, the following figure shows the condition of off state of Zener diode, where no current flows through it and the voltage is V and it is less than V Z. So, it is a off state for the Zener diode. So, during the off state, the following values will be obtained for current and voltages. The current I will be equal to the I L, that means when I Z is equal to 0, since no current is flowing through the branch of the diode current because it is at off condition. So, I will be equal to I L and VR will be equal to EI minus E naught, and V is equal to E naught when the value of V is less than Vz. So, here important point is that the voltage V will be equal to E naught when it is less, the value of V is less than Vz. So, the power dissipated in Zener diode will be Pz equal to V into Iz. So, since Iz is equal to 0, therefore, the power dissipated in the Zener diode will be 0. Now, let us see the analysis of Zener diode for second condition. The second condition is fixed source voltage EI and variable load voltage RL. So, here one value is fixed, that is the source voltage EI is fixed, but the load is varying, that means the resistance across the load is varying. So, let us do the analysis for the Zener diode for this condition. So, the figure is showing the circuit diagram where the source voltage is kept fixed and the load side is varying, showing by the variable resistance RL. So, here the applied voltage EI is fixed while load resistance RL and hence load current IL changes. So, as the load is changing, that is resistance, load resistance is changing or it is variable. So, depending upon that the load current will also change. So, IL will not remain constant, it will depend upon the value of RL, that is the load resistance. So, point here to be noted is that since the value of RL is variable, but it will vary within a specific limit and hence the current will also vary within those limits. As we all know, any semiconductor device or any electronic device or any electrical device, they are having a maximum or minimum limit, whether it is of current limit or voltage limit. So, the resistance, the load resistance connected here, although it is a variable quantity, but it will vary within certain limit. So, depending upon that limit, the current obtained will also have a certain limit. So, it will vary within those limits only, and if it crosses that limit, that can damage the diode or the complete circuit also. So, the range of values obtained here will be RL minimum and IL max, and second value will be IL minimum and RL max. So, this value will obtain in such a way that when the resistance at the load is minimum, the current flowing through will be maximum, and when the current is minimum, the resistance will be maximum. So, we will discuss these two conditions in more detail. So, let us discuss the first condition, that is when the resistance is minimum and the current is maximum at the load side. So, once the Zener is in on state, the load voltage E naught will be equal to Vz, which remains constant. So, due to this, when load resistance RL is minimum, the load current IL equal to E naught upon RL will be maximum. So, in order to find minimum load resistance which will turn the Zener diode on, we simply calculate the value of RL that will result in E naught is equal to Vz. That is, when Zener in the circuit is removed, then the value of V will be equal to RL into EI divided by R plus RL. So, by this voltage we will find out the value of RL, the minimum value of RL for which will turn on the Zener diode. So, the value of E naught will be equal to Vz and it is equal to V, and the numerical value came here will be equal to RL into EI divided by R plus RL. Therefore, the value of RL minimum will be equal to R into Vz divided by EI minus Vz. So, this is the minimum value of load resistance that will ensure that Zener is in the on state. Any value of load resistance less than this value will result in a voltage E naught across the load less than Vz, and Zener will be in the off state. We are studying the condition for RL minimum, so it again has a particular limit. So, the minimum value of RL should be such that below which the Zener will be in off state. So, the minimum value be such that value should keep the Zener in the on condition, and if the value goes below that, the Zener will come into off state. So, clearly from this we can find out that the value of current IL max is equal to E naught divided by RL minimum, and it is equal to Vz upon RL minimum. Now, the second condition is this condition is for fixed value of source and variable resistance. So, in this we are discussing the second condition, which is when the current is minimum and the load resistance is maximum. So, the Zener current here is Iz is equal to I minus IL. So, when the Zener is in the on state, I remains fixed. This means that when IL is maximum, Iz will be minimum. Now, on the other hand, where IL is minimum, Iz is maximum. So, if the maximum current that a Zener can carry safely is denoted by Izm, this value comes from the maximum power dissipation, that is Pzm equal to Vz into Izm. So, the maximum current that a Zener can carry is denoted by Izm. Therefore, IL minimum will be equal to I minus Izm, and from this the value of RL max will be equal to E naught upon IL minimum, which will be equal to Vz upon IL minimum. So, if the load resistance exceeds this limiting value, the current through Zener will exceed Izm and the device may burn out. Load resistance, it has a maximum limit, and if the value crosses beyond this limit, it will damage the Zener diode. Now, let us discuss the third condition, that is fixed resistance RL and variable EI. So, let us do the analysis for Zener diode when the source voltage is variable, but the load resistance is kept constant. So, the figure showing the circuit where the source voltage EI is variable, which is varying within a certain limit, and the resistance, the load resistance is kept constant. So, in this condition, how the Zener diode will work, we will discuss it in detail. So, here the load resistance RL is fixed and the applied voltage EI changes. So, it is to be noted here that a definite range of EI values should be kept or should be ensured, so that the Zener diode is in on state. So, here the condition arises is that even if the value of EI is varying, but it should be varying in certain limits which ensure that the Zener diode is in on state. The value of EI crosses that limit, the Zener may come from on state to off state. So, there is a limitation, or we can say that there is a limit within which the value of EI can vary. So, let us see the two conditions, that is the maximum value of EI and the minimum value of EI for which the Zener diode is kept in on condition. So, let us start with the minimum value, that is EI minimum. So, to determine the minimum applied voltage that will turn on the Zener, simply calculate the value of EI that will result in load voltage E naught is equal to Vz, which means that if we have to find the minimum value of EI, we have to find the value of E naught for which its value comes out to be Vz. So, that value will be the minimum value for which the Zener is in on condition, and it is giving the voltage Vz as Zener voltage, and it is equal to the output voltage. So, E naught will be equal to Vz, and from the circuit the numerical value comes out to be RL into EI divided by R plus RL. Therefore, the minimum value of EI will be equal to R plus RL into Vz divided by RL. Now, the maximum value of EI, it is denoted by EI max. So, now the current through R will be I is equal to Iz plus IL. Since IL is equal to E naught upon RL, or it is equal to Vz upon RL, which is fixed, the value of I will be maximum when Zener current is maximum, that is I max is equal to IZM plus IL. Now, EI, that is the source voltage, it is equal to I into R plus E naught. Since E naught is equal to Vz, which is a constant value, therefore, the input voltage will be maximum when I is maximum. So, from this we can find out the maximum value of source voltage, which is equal to EI max equal to I max into R plus Vz. So, this will give us the maximum value of source voltage. So, from this we have obtained a limit, that is EI minimum and EI max, and the source voltage should lie between these values when this load resistance is kept constant, and by keeping the value of EI within this limit, we can ensure that the Zener diode remains in the on condition. Now, let us discuss some numerical. A figure is shown here, which is a circuit for a Zener. In this, the source voltage is 120 volt and the load resistance here is 10 kilo ohm, and the voltage, that is Vz, Zener voltage is given here is 50 volt, and the resistance connected in series is 5 kilo ohm. So, for this we have to find first the output voltage, and second the voltage drop across the series resistance, and third the current through the Zener diode. So, for this the given next circuit is showing the equivalent diagram for the circuit, in which the Zener is replaced by its voltage, that is Vz equal to 50 volt, and we have to find the output voltage. So, the Zener diode in the figure, the voltage V across the open circuit is given by V is equal to RL into EI divided by R plus RL, where R is the series resistance and RL is the load resistance. So, the value will be 10 into 120 divided by 5 plus 10, and it comes out to be 80 volt. So, since the voltage across the Zener diode is greater than Vz, that is equal to 50 volt, since the voltage mentioned in the question is 50 volt and the value of V coming out to be greater than 50 volt, therefore, the Zener diode is in on state. So, therefore, it is represented by a battery of 50 volt as shown in the second figure, that is the equivalent circuit of the Zener diode. So, the output voltage Vz will be equal to 50 volt. Since the Zener is working, so the output voltage E naught is always equal to Vz whenever the condition. And next is the voltage drop across R. So, it is found out by the input voltage minus Vz. So, the input voltage here is 120 volt and the Zener voltage is 50 volt. So, the voltage drop across R comes out to be 70 volt. And last is the load current IL. It is calculated by Vz upon RL. Since the value of Vz is 50 volt and the load resistance is 10 kilo ohm, so the value comes out to be 5 milliampere. So, the current through the load R is I, and it is equal to 70 volt divided by 5 kilo ohm, and it comes out to be 14 milliampere. So, applying Kirchhoff's law, I is equal to IL plus IZ. So, from this we can calculate the Zener current IZ equal to I minus IL, which comes out to be 14 minus 5, which is equal to 9 milliampere. So, here we can conclude this thing from the numerical that the voltage for the Zener, that is Vz, was given, which is equal to 50 volt. So, from that we have checked for the given circuit the voltage value V. So, it is coming out to be 80 volt. So, from that first we have concluded that the Zener is in on condition, since the value of V is greater than Vz. So, the output voltage was 50 volt and the drop across the R was 70 volt, and by applying the Kirchhoff's current law in the circuit, we have obtained that the Zener current flowing is 9 milliampere. A circuit is shown which is having a variable source. The source voltage is varying from 13 volt to 16 volt, and it is having the variable load also, and since the variable load is shown, that means the value of RL will be varying, and due to this RL the current, load current will also varying. So, a range is given for the load current, that is 10 milliampere to 85 milliampere. So, in the circuit the value of Vz is shown to be 10 volt, and the Zener current, the minimum Zener current is given as 15 milliampere. So, we have to find the value of R, that is the series resistance connected in the circuit. So, in this type of question we have to apply certain concept. So, here the condition applied will be the Zener will conduct minimum current, that is 15 milliampere when the input voltage is minimum, that is 13 volt. Okay. When the minimum current is given for the Zener, that is 15 milliampere. So, that will obtain with the minimum supply voltage, that is the 13 volt. When the minimum voltage is applied, that is 13 volt, since the voltage is in varying condition. So, applying this values, the value of R can be calculated from EI minus E naught divided by IZ minimum plus IL maximum. So, the maximum current which can flow is 85. So, the value comes out to be 13 minus 10 divided by 15 plus 85, which is 3 divided by 100 milliampere, and from this we obtain the value of R as 30 ohm. So, by applying the concept of the maximum current and the minimum current and the maximum source voltage and the minimum source voltage, we can derive the formula from the circuit, and in this case we have derived the formula, that is R is equal to EI minus E naught upon IZ minimum plus IL maximum. So, the value obtained here is 30 ohm for the series resistance. So, from this we can find out the different values of resistance and the current or the voltages for different conditions by applying the concept of Zener for the varying voltages or the varying load. So, in today's lecture we have studied about the Zener diode as voltage regulator. We have studied different conditions for the analysis of Zener diode, and we have discussed certain numericals from which different conditions are applied to calculate the values of resistances or current. Thank you.